So good evening, everyone. Welcome to this session on Foundation to Lithium-ion Cell Testing. So my name is Abhinav Arvind, and currently I'm working as a battery algorithm development engineer at Decibels Lab. I'm also involved in developing battery management systems for lithium cells, and I'm also working on cell testing equipment where certain cells of different chemistries are being tested, and later on their data will be utilized in order to develop battery management systems. Yeah. So today's course content includes these following topics. So first, we'll have a look at a brief definition of cell testing. So what is the essence of cell testing, right? We'll take a look at some of the cases or some of the scenarios that cells can face, yeah, in real life. Then we'll go ahead and see what is the need for cell testing. Why is cell testing needed? And what is the necessity of cell testing? And then we'll go and take a look at cell data sheet. So we'll have a brief look at what is a cell data sheet. And then we'll go into some cell testing methods, yeah, where we'll take a look at three categories of cell testing. So these three are performance tests, physical abuse tests, and life cycle tests, are also called aging tests. And then after this, following this, we will also look at cell testing standards. So there are so many cell testing standards, and we'll have a look at some of the most majorly used or widely used cell testing standards in today's EV market. Yeah. And then we'll also take a look some of the testing equipment. So the testing equipment used here at Decibels Lab, and also some of them used in different industries. Yeah. And then we'll have a look, we'll take a final overview, right? And then we'll see what is the future scope, a brief look at what is the future scope of the cell testing. Yeah. So with that, we will now begin with introduction to cell testing. Yeah. So, briefly defined, cell testing is basically taking any cell, any electrochemical cell, and then subjecting that cell to different situations, different scenarios, and different conditions to evaluate and to analyze its performance, reliability, safety, and different failure points or different failure modes in each situation or in each condition. Yeah. And these situations could be presented in different scenario, different ways. Starting with some very common ones where we have varying temperatures, yeah, varying ambient temperatures. So it's like, consider Chennai. The temperature there is completely different. The environment there is completely different compared to what you would see in the Himalayas, in the northern part of India. Yeah. So how would a cell behave in that scenario? How would it behave in different temperatures? Okay. So how different is its behavior in Chennai or in South India compared to how it would be in the mountainous regions? Yeah. So these are some of the scenarios which have to be considered in a real life behavior of a battery. Yeah. So not only that, but we also have varying pressures. So varying ambient pressure, right? So this pressure would mainly change in altitude. So again, at sea level versus at higher levels. Yeah. At hill stations versus what it would be at on higher mountains. Yeah. And then different humidity. So what that means is different moisture content in the atmosphere. So if the place is continuously experiencing a lot of rain, or if the place is extremely dry, yeah, or if it's a place like here in Bangalore where there's a good balance between rain and sunshine and humidity as well. So how would a battery pack perform, or how would the cell perform in this kind of a scenario? That has to be analyzed. Yeah. And then also coming to physical disturbances. So we took a look at environmental disturbances. Now we can take a look at physical disturbances. So that would come from three different scenarios or three different situations. So one would be from vibrational. So that would fall under mechanical. Okay. So please pardon me for the handwriting. So vibration comes under mechanical disturbances. Thermal shock would come under thermal disturbances. Right? And electrical malfunctions would come under electrical abuse. Okay. So this would come under electrical abuse. So these three are the main scenarios, or the main disturbances, physical disturbances that a battery or a cell would face in real-time operation. Yeah. So we will have a brief look at all of these scenarios, how exactly that influences battery behavior, and why and how exactly cells are tested in these situations. Yeah. We'll also have a look at overcharging and discharging, right? So basically cells, whenever they are uh, and experiencing overcharging. So it's like if the charger is working more than what it's supplying more current than what is necessary, or if the battery is discharging more current or is supplying more current than what is necessary, then how will the cell behave? Yeah. And also we come to dewing and condensation. So this would be in extremely humid environments. And also there is another classification of this called as a submersion test. Okay. So where the battery pack will be submerged under water. Okay. So this is another form of abuse. Okay. But this would come purely under uh, abuse due to water or abuse due to high humidity. Yeah. And then also another situation which cells could face in real life is failure of protection systems. So battery management systems are not 100% perfect always. Yeah. So they could fail at some point in time. Yeah. So suppose its current protection could fail at any point, or if its voltage limiter could fail at some point, its short circuit protection could fail at any point. So in those situations, in those extreme situations, how would the cell behave under very challenging situations or very high task situations? So that is also some of the cases that the cell could face. Yeah. And then finally we come to overheating, right? This is where the cell is experiencing extremely high temperatures above and beyond its safety limit, right? So by subjecting the cell to all these different situations, or by subjecting the cells to all these different scenarios and conditions, one can understand how a cell would behave in these situations. Yeah. So that is what is cell testing, where a particular cell, it does not matter exactly which cell it is, whether it's lithium ion, or even if it's lead acid, or if any such cell, if it's subjected to all of these situations, then the designer, the battery designer or the engineer can have a clear picture as to how it would respond, right? And based on this, keeping these in mind, we come to the need for cell testing. Yeah. So keeping all these situations in mind, we can then understand the following: that what are the limits of operating the cell, yeah, in terms of voltage, in terms of current, in terms of charging, discharging limits, capacity, energy, power, voltage windows, and varying atmospheric conditions, right? So these are all different situations or different limits that a cell can face, and even the entire battery pack, not just one cell but the entire battery pack would face. Yeah. And then by performing the testing, this is what one would be able to understand. So that's the first and foremost thing. Following this, we'd be able to understand the real life characteristics and behavior of the cell in cell level, module level, and pack level. So it's so a battery pack is like categorized in three levels. So one is cell level. So that would be one individual cell. Yeah. And a group of cells would then make a module, and a group of modules would then make a battery pack. So testing would then help understand what are the characteristics and behavior of the cells in individual level or in singular level, in the module level, and in the pack level. Yeah. And then we then be able to understand and analyze battery pack failure modes, right? So battery pack failure modes is something that's very, very crucial in order to understand what are the different ways and what are the different situations they could fail in, and then accordingly design for failure. Okay, so this comes under something called as DFMA. Okay, so this is a very common practice. It's called design for failure mitigation and analysis. So all systems, right? So irrespective of whether it's a battery or even if it's a structural element or whatever it is, they are all analyzed for different failure modes, and then accordingly the design for failure and mitigation is established for this. So by analyzing when the battery pack fails, right, and how the battery pack fails, the engineer can accordingly design for failure, right? And as a consequence to this, also we can introduce all the necessary safety devices, safety circuits, and safety systems in all the levels, so cell, pack, and module level, and introduce certain algorithms, fail-safe algorithms, which prevent such situations from occurring again. Yeah. Then we'll also be able to predict and analyze cell aging. So we know that upon repeated usage, cells will start to degrade, right? Internally, the cells will start to degrade their electrodes, your anode, cathode, your current collector, separator, your electrolyte, all of these materials, all of these components inside the cell will start to age. And we'll be also be able to establish a good understanding of state of health and also life cycle. Okay, so this is something very important. This gives a very good estimate as to how many years can a particular cell last in the market, right? So we know that in today's in the EV market, people demand there to be a very high life cycle age where it has to run thousands and thousands of cycles. So this is exactly what cell testing helps us understand. Yeah, this is why cell testing is needed, so that we are able to understand how quickly the battery or how quickly the cell is degrading. Yeah, and how quickly, I mean, how long it would last, given the certain situations it's facing. And then we can also analyze the effects of physical damage, such as shocks, impacts, vibrations, damage, cracking, rupturing, things like these, and how exactly the cell would again behave in these situations, right? So let's say if a cell is cracked open and certain amount of the material inside has leaked out, would it be still an hazard to the environment, or would it still be safe, relatively safe, right? So all this can be understood. And then finally, based on all these points put together, all of these points put together, we come to the final one where, understanding and analyzing all of these points, together, we can modify the performance and behavior. We can tweak the performance and behavior to get the maximum operational efficiency and also operational life from the cell. Yeah. So this is the need for cell testing. This is what cell testing helps one understand how exactly a cell would behave and why exactly certain situations or certain conditions can influence certain behavior aspects of the cell. Okay, so with this in mind, we will now move on to understanding a simple cell data sheet. Yeah, so here you can see this is for a lithium LiFe. So I will write down the chemistry here. So this is a data sheet for a lithium lithium ferrophosphate, so LiFePO4. Okay, so this is a data sheet corresponding to this cell chemistry. Yeah, and so first and foremost, we'll start off by looking at the nominal capacity. Yeah, so the nominal capacity is the capacity of the cell that is obtained if you discharge the cell at 0.52 amps. Okay, so this is called nominal discharge current. And if you discharge the cell at this particular current rate, then you would obtain a discharge capacity of 2600 mAh. But usually you see 2600 mAh is not always obtained. Yeah, this is more or less the rated capacity. But what is actually obtained would be something realistically like 2500 or 2550 mAh. Yeah, so that would, again, that this is because of the losses, the internal losses that the cell continuously faces. Yeah, so in realistically, if you were to discharge it at around 0.52 amps, then you would obtain a discharge capacity of 2500 to 2550 mAh. Yeah, so that is the first and foremost thing. And this would be fixed at a temperature of around 25 degrees Celsius. So then again, its capacity would change at different temperatures, which we will take a look at in the upcoming slides. So we will see how exactly the capacity would change in different temperatures. Yeah, and then we look at the next one, which is called nominal voltage. So the nominal voltage, you can see here, the nominal voltage is nothing but the voltage of the cell if you were to consider it at 50% charge or 50% percentage, 50% capacity. So if you were to measure its voltage exactly at this charge, yeah, then you would be able to see that lithium chemistries typically give you around 3.7 to 3.8 volts, yeah, nominal voltage. So that's what nominal voltage means. Then internal impedance is the collective internal resistance that the cell has. Yeah, and that it is important that it is as low as possible, so that it not only has lower losses, but also that it doesn't experience excessive heating during operation. Yeah. So then we come to discharge cutoff voltage. So during operation, 3 volts is accepted as the minimum voltage that the cell could reach. So which means that during discharge, if it crosses 3 volts, the cell should immediately stop working, or it should immediately be isolated from the particular circuit. Yeah. So that is what discharge cutoff voltage means. Yeah. And then we come to maximum charge voltage. So just like discharge cutoff voltage, so when the cell is being charged, the maximum voltage will be 4.2, and crossing that would mean, once again, operating outside the cell's designed area, or cell safe designed area. Yeah. So then we come to standard charge current. So if you were to charge the cell at 0.52 amps, then it would give you a good charging efficiency. Yeah. So higher the amount of current you supply, the more the losses and lesser the efficiency of operational efficiency of the cell. Yeah. We will have a look at this in a particular testing scenario, where test cell will be tested at different discharge current rates and as such. Yeah. So then the next one, rapid charge current. So what that means is a current of 1.3 amps maximum can be supplied to the cell safely without there being any damage. That's what this particular term means. And similar to the standard charge current, we also have a standard discharge current. So that is of the same value, and same with the rapid discharge current. So again, it can be safely discharged at 1.3 amps, and anything higher would start to degrade the cell quickly. Yeah. And there's another type of current. It's called pulse current. So what that means is you can draw pulses of current from the cell, and usually they are much higher than your maximum current. So what you see here, point number 5.8, is your maximum value. Okay, maximum continuous value. Okay, so this is a maximum continuous value. So that is your discharge current. And what you see here, yeah, this is called as the peak value. Okay, so there's a difference between the two. What this means is that usually this is safe. Okay, this value is safe, and this value is unsafe. So what that means is discharging it at 2.6 amps, even if it at pulses, would mean that you're basically forcing the cell to work outside its capability. So that's what is the difference between these two. Yeah. And also that you can only draw this current in pulses, not continuously, right? And then we come to the dimension. So dimension classification is typically for a lithium ion cell would be a classification called 18650 or 18650. So what that means is that the cell is 18 millimeters in diameter, 65 millimeters in height, and the 0 at the end means it's a cylindrical cell. Yeah. So a cylindrical cell with 18 millimeters diameter and 65 millimeter height. Yeah. So these are then the operational temperature limits. So during charging and discharging, it has to be ensured that this two values are always kept, so that the cell does not start to get damaged if it starts to function outside these areas, these limits. Yeah. And then finally we come to storage temperature. So storage is basically like isolated condition where the cell is just kept in a particular storage device or a storage facility, and it has to be the amount of the temperature that we set inside is dependent on the duration of storage. So if it's for 1 month, it would be a more flexible temperature range, but if it's for a much longer time, then it has to be kept in a much shorter duration or a much shorter temperature limit. Yeah. So this is a brief look at the cell data sheet, and whatever testing is done based on the benchmark values that have been obtained over here. Yeah. So now we will take a look at the different testing requirements, right? So it is required by any manufacturer, irrespective of what application it is, to perform all these 3 tests, right, in a particular cell. So whether it's from lithium ferrophosphate, or if it's from lithium aluminum cobalt, or lithium nickel manganese cobalt dioxide, or whichever chemistry it is you take from lithium, it is mandatory for any manufacturer to perform these three tests, yeah, and then undergo a final test called as an acceptance test. Yeah. So what that means is, if the cell that is being tested undergoes all of these and satisfies all of these requirements, it would then undergo something called as an acceptance test, and then it would be approved of roadworthiness. What that means is, it is then worthy of being used in any EV application. Yeah. So this is a brief look at all of these minimum criteria that all of these tests have to be performed. Yeah. So in today's session, we will take a look at the first one. So static capacity test at different temperatures, and also at room temperature. And then we will also take a look at the static capacity test at different C rates. Yeah, what that means is at different current rates, right? Then we will take a look at something called as pulse power characterization, or power characterization. This one, the third one, right? That is in performance tests. Then we will take a look at abuse tests. So we will take a look at thermal shock cycling, vibration, and also short circuit test. So this is with respect to abuse, physical abuse. And then with respect to life cycle and aging, we will take a look at SOC loss due to storage, and also uh, capacity loss due to cycle life. Yeah. So these are the different performance, different tests that have to be performed in a particular cell. Yeah. So we will now take a look at the first one. So the first one is static capacity test at different C rates. Yeah. So what that means is that a particular cell will first be kept at a room temperature of 25 degrees Celsius, right? It is so that there is no disturbance inside the cell, and that it achieves both thermal and chemical equilibrium. So the chemical reactions inside are steady and are not, fluctuating in rate, or not fluctuating in magnitude. Yeah. So that's the first step, that it is first allowed to be stabilized at 25 degrees Celsius, and then it is discharged at different C rates or at different current rates. Yeah. So on the left hand side, you can see a graph that shows the voltage curve of a cell. How exactly the voltage curve would vary if it were to be discharged at different C rates or at different current rates. Yeah. So starting with the first one, the blue one over here, this blue one. So this is a voltage curve corresponding to very low discharge currents. Yeah. So what that means is, the cell would be discharged at very low current rates. So it is usually represented in C rate. Yeah. It is usually represented in C rate. Yeah. So C rate is nothing but the ratio between the amount of current drawn or amount of current supplied to the cell with respect to its capacity, which is given by Q. Yeah. So this is a typical 2600 mAh cell. So a capacity, a current of 0.3 C would mean a current of 0.78 amps. Yeah. So if I take a current of 0.78 amps, and then I divide it by the capacity of the cell, so that's 2.6 amp hours, I would then get the C rate. Okay, so that would give me roughly 0.3 C. Yeah. So that means a current of 0.78 amps is continuously discharged from the cell. Yeah. And this is the voltage curve that you can expect to see once it is discharged at this particular value. Yeah. So it starts at around 4.2 volts. Yeah. And ends roughly at around, you can see here, 2.8 volts. That is the safe minimum discharge voltage. Yeah. So likewise, discharging the cells at different C rates would give you different voltage bands. So these are different voltage bands. So you can see them in different colors. So yellow, purple, green, and then finally light blue, and then we have red, and then we have brown. Yeah. So these are different voltage bands you would be able to observe if you were to discharge the cell at different C rates or at different current rates. Okay, so higher the current rate, you can see here, the further down we go, the higher the current rate. That means higher the amount of current being drawn from the cell. Yeah. So the last line that you can see, the brown line, it will give you a very low capacity. While if you were to discharge the cell at low current rates, it would give you a higher capacity. Yeah. So this gap in capacity over here, this gap in capacity, okay, this is called capacity fade. Okay, so this gap in capacity is called capacity fade. Okay, so this capacity fading occurs because of one main thing, because that at higher current rates, right? So usually at higher current rates, the chemical reactions inside the cell are not able to go to its fullest extent, which means they are not able to complete fully. Yeah. So so because of that, there would be some loss, some high amount of losses occurring inside the cell, and that can cause a drop in the discharge capacity or the available capacity during operation. Yeah. So by performing this test, right? So what that is nothing but the main objective of this test is to obtain first and foremost the discharge capacity of the cell at different C rates, right? And the second thing is to analyze to what extent capacity fade is occurring. Yeah. So the extent of capacity fade. So extent of capacity fade. I will just abbreviate that as CF. So CF is capacity fade. So again, as I said, capacity fade is nothing but a phenomenon where the cell is not able to give out its true capacity or is not able to give out its typical capacity because of losses that take place at higher current rates. Yeah. So higher the amount of current being drawn, higher the amount of losses taking place within the cell. Yeah. So because of that, you can see at higher C rates or at higher current rates, especially if you go down to like 1.5 C or even higher than that, right? You'll be able to see that there are some pretty severe losses occurring. And then because of that, there's a lot of capacity loss or capacity fade. Yeah. So in essence, if you were to take a cell and if you were to continuously discharge it and continuously, if you were to discharge it at very high C rates, then you would have a permanent loss in capacity. Yeah. So what that means is after a number of times of discharging it at high C rates, your starting voltage, yeah, or your maximum voltage would come down to something like 3.9, yeah, or something like 3.8, and then your capacity graph would then drop to like this point. So that much capacity has been permanently lost, which means it cannot be regained no matter how much you try to like repair the cell, or no matter how much time you try to rectify the internal working of the cell, right? So what that means is permanently this much capacity is lost. So that's around 0.6 amp hours capacity is permanently lost. Yeah. So this test tells us the discharge capacity of the cell at different C rates, and also the extent of which capacity fade can occur due to high C rates. Okay. So there is also another capacity fading that can occur, and that is because of temperature, which we will take a look at in the next slide. Yeah. So this is the same test, but at different temperatures. So in the previous test, we saw that the temperature was fixed, right? But in this case, temperature is varied, but the amount of current being discharged from the cell will be fixed. Yeah. So this is again the same cell. So it's a 2600 mAh cell, but here the amount of current being drawn is fixed. Yeah. So here we can see a graph on the left hand side that shows the voltage bands or the voltage curves that can be observed at different temperatures. So here at low temperatures, you can see it gives out very low capacity. Yeah. And even the starting voltage of the cell is quite low. Meanwhile, you can see that at higher temperatures, you have a much more active cell. It's able to give out much more capacity. It's able to withstand much longer. Yeah. So the reason for this is pretty simple. It's just that at lower temperatures, the electrolyte inside starts to freeze, and therefore its ability to conduct ions starts to rapidly deteriorate. Yeah. And that is why you can see that even though the cell is in pretty good condition, it would not even be able to start at 4.2 volts, and it would just drop directly even below its nominal voltage region and just not even give out 50% of its capacity. So it just dies out pretty quickly. Yeah. So meanwhile, you can see at higher temperatures, if the cell were to be like tested at 40 degrees or even higher, it would be able to conduct ions in a much better way. Again, because the electrolyte is able to perform much better, and also that the ions inside. So there are certain ions that are produced at the electrodes, at the surface of the electrodes, and those ions will have higher energy, yeah, to overcome the resistance inside. Which is why you can see the cell at higher temperatures is able to give out much more capacity. Yeah. So that is the difference between using the cell at high versus low temperatures, right? And the objective of this test is to determine the discharge capacity of the cell at different ambient temperatures, which is one thing, and the second thing is to observe and analyze what is the extent to which capacity fading would occur if it were to be subjected to different temperatures. Yeah, so low versus high. So it's not always advantageous that you use it at high temperatures, right? So one thing which we all know is that the lithium ion cells is like very famous for something called a self ignition or thermal runaway. Yeah. So this particular phenomenon is pretty dangerous if you were to expose the cell to higher temperatures, and that can cause your electrolyte to start vaporizing inside. Yeah. And that can cause the cell to catch fire. So which is pretty dangerous if you were to take it to higher temperatures like 60 degrees. Yeah. Which is why usually for lithium ion cells, 60 degrees is like the upper operational limit. So usually it would give pretty good performance, but then also one has to consider the safety factor while operating the cell. Yeah. So this is static capacity test at different temperatures. So here we can observe the different voltage bands at different temperatures. Yeah. So the higher you go, the more conductivity the electrolyte has, and the more capacity it's able to give out, right? But also the higher the risk of catching fire. Yeah. And higher the risk of also like interior degradation. So the cell also starts to degrade inside this within itself. Yeah. So that is with respect to static capacity test at different temperatures, right? And one of the major tests performed on any lithium test is something called as pulse power characterization. Yeah. So this test helps us understand two things, right? It helps us to give a good estimate as to what is the resistances the cell faces, okay, and what is the dynamic performance characteristics of the cell at different voltage voltage stages. Yeah. So we know that as and when the cell is discharged, we know that it will be having like the voltage is not one single reading, it keeps changing, right? So at each voltage interval, what would be its possible performance characteristics, and it'll also help us determine what would be also the power fade that occurs over extended usage. Yeah. So it's all about performance. This is purely a test done to understand the complete performance and the performance band of the cell. Yeah. So what is usually done is that the cell is subjected to different pulses, okay, of current. So usually it starts with the cell at open circuit voltage or at no voltage situation, and then it is subjected to a discharge current. Yeah. And then it is subjected to a charge current. So that is one pulse, right? And then it is subjected to another discharge pulse. Yeah. So this is usually the profile of the pulse power characterization test. Okay. So now we'll try to understand what each one means. So this discharge and charge pulse is meant to usually meant to see how quickly the cell can respond to this kind of a scenario. Yeah. Right. And each pulse lasts for 10 seconds. Yeah, as per testing guidelines, as per any testing guidelines. So whether you take different guidelines, they will all have the same guidelines, and they will all say that the amount of time that the pulse is needed to be supplied is for a minimum of 10 seconds. Yeah. And following this pulse, there is another discharge pulse. Okay. So which is meant to remove 10% of the capacity of the cell. Okay. So 10% capacity or 10% charge. Okay. So this particular cycle is repeated over and over again till the cell reaches from 100% charge, okay, to 0% charge. Okay, it's performed like this because the initial pulses that we see here is determined in order to see how much time it takes for the voltage to respond, or it take to determine how much time the cell takes in order to respond. Yeah, so that is observed in the voltage graph, which I will come to in just a minute. Okay, that's what is the importance of this pulse. It helps determine, or basically it is to analyze how quickly the cell would respond to this kind of a pulse input. Yeah, and then once we come to the next discharge pulse, so this one, yeah, so this one is basically meant to remove 10% of the capacity. So which means it's then brought on to the lower battery life. So for example, let's say it's charged up to 100%. So then this pulse would then remove 10%, and then it would become 90%. Yeah, and then the same pulse is applied, and then its response at that particular battery percentage is observed, and then once again 10% is removed, so 90% then would become 80%. Yeah, so at each different percentage of charge or a different percentage of capacity, the same pulse is applied, its voltage response is observed, and then some more 10% is again removed all the way till it reaches 0%. Yeah, so by doing this kind of a test, its dynamic characteristics are understood, its voltage behavior is understood, and also the polarization, I mean to say the different kinds of resistances that the cell has will be able to be estimated. Yeah, so just briefly I will explain what is the type of internal resistances that the cell can face. Yeah, so one is called as ohmic resistance. Yeah, one is called as ohmic resistance, and one is called polarization resistance. Yeah, and the other one is called activation resistance. So these are the three different types of resistances that the cell can face. I will not be going too much in depth into this because it requires a lot of explanation, but simply explain, these are the three different types of resistances that the cell can face. And using this method, these three resistances can be understood, or these three resistances can be estimated. And overall, like even it can be estimated how much resistance change occurs over the number of cycles of the cell. As and when the number of cycles that the cell experiences goes on increasing, the change in resistance can also be estimated. Okay, so that we can also take a look at aging tests, which I will explain in just a minute. So this is with respect to pulse power characterization, and here you can see on the bottom right hand side, this is the voltage response of the cell. So from the voltage response and from the current pulse input that we give, we'll be able to understand the amount of resistance and also the dynamic performance of the cell. Yeah, so this is with respect to pulse power characterization. Then we come to abuse tests. Okay, so the first one we will look at is thermal shock cycling. So what that means is that a battery pack is subjected to varying ambient temperature. So starting from minus 40 degrees Celsius to 80 degrees Celsius, the temperature change occurs, and the battery pack will be subjected to this kind of a temperature change. So this is a rapid temperature change, and it occurs within 30 minutes of time interval. Yeah, and this will be gone. It will go on repeating for a minimum of 5 times. So what that means is minus 40 to 80, and then 80 to minus 40 is one cycle, right? So that would be repeated 5 times, and then the analysis is, it would then be understood how the battery would perform in this kind of a stressful environment. Yeah, so the goal is to understand how the cell would behave in a highly thermally stressful environment, right? So you can see this is the ambient temperature. And this is just a thermal image of how the entire battery pack would behave if subjected to some very, very high temperatures. Yeah. So here you can see how exactly the temperature distribution is here on this side. So it is basically a thermal abuse test, right? And then a couple of things will be observed here. So the first important thing is that does the battery pack or does any individual cell start to exhibit overheating? Yeah. So does it exhibit overheating? Yeah. Does it exhibit or does it experience any overheating? And as a consequence, does it experience any ignition? Ignition means does it catch fire? Okay. So this is the primary objective of this test, right? So these two criteria are looked at. If at any point in time the cell begins to overheat, what that means is that if the cell starts to act outside its safe temperature zone, or that if it's not cooling enough, right? Or if it catches fire, so that means that the cell is not, I mean to say, if the battery pack is not approved, and therefore it is not accepted as a roadworthiness device or a roadworthiness system. Yeah. So it has to satisfy no overheating and no ignition. So if it displays no overheating and no ignition, that means that the battery pack has undergone the acceptance requirements, and then it would then become roadworthy. Yeah. So that is thermal shock cycling. So shocking means basically to rapidly change the temperature, and cycling means to continuously change, continuously make this particular battery pack undergo this variation in temperature over and over again. Yeah. And then we come to vibration tests. So vibration test basically is done to understand how the battery chemicals inside would behave in a different vibrational situations. Yeah. So you can see this is a vibrational test setup here. Yeah. And this is the test bench. This is a test bench manufactured by Crystalline Instruments. So they're one of the world's leading manufacturers of vibrational testing equipment. Yeah, especially for EV battery packs and hybrid electric vehicle battery packs. Yeah. So this particular battery pack is mounted onto this bench, and then it is subjected to vibrations in three directions. So X, Y, and Z. So this is one direction, this is one direction, and this finally is the vertical direction. So longitudinal, which is X, and transverse, which will be Y, and vertical will be Z. Okay, so it is subjected to 200 hertz worth of vibration, 200 hertz frequency of vibration in all three directions for a duration of 12 hours. Yeah. So this is the particular operation, vibrational operation or vibrational test that the battery pack will undergo. Yeah. And the aim or the objective is to again analyze the behavior of the battery pack in these harsh situational and vibrational situations. Yeah. And at the end of testing, if there is no venting or if there is no excessive gases being produced from within the cell or from within the battery pack. So basically gassing means that there is some amount of chemical reactions that occur which can cause gases to be released. Yeah. And that's a pretty dangerous situation. It can cause explosion, or it can cause like the battery to become it can cause the battery to stop working. Yeah. So at any point in time, if there is no venting or if there is no gassing observed, yeah, or if there's no leakage of chemicals, no change in or no loss in mass, no damage, and no fire or no explosion. So if all these criteria are satisfied, then it would become roadworthy. Okay, so that means it has undergone the acceptance criteria, yeah, and it is roadworthy. So likewise, different battery packs of different sizes and of different capabilities will be tested. And usually the vibration would be limited to 200 hertz simply because of the mass of the battery pack. So the higher the mass, the more the stress is given onto the machine as well. Yeah. So for that reason, it is limited to 200 hertz. And after the test, it will be accepted based on this criteria that we see here. Yeah. So this is what is the vibrational test. And then we will also come to short circuit test, which is an electrical abuse test. Okay. So in this, it's the battery pack or a pouch or any cell is connected to a wire of very low resistance. So this is the wire that you see here. Okay, so this wire is having very low resistance of around 0.1 ohms. Okay, 0.1 ohms. Okay, so the purpose is that this wire at such low resistance will then begin to act like something called as a shunt wire. Okay, so we know that the term shunt means very low resistance. So this pouch or this battery pack that we see here is connected to this very low resistance wire, and what happens is the cell is then allowed to discharge at very high current rates through this shunt resistor. Yeah, and then two things are noted. Is there any short circuit? So what that means is there any shorting happening at the battery terminals? Yeah. So that means that is there any massive surge in current? So short circuiting basically means a very huge surge in current. Yeah, especially at the terminals of the battery. That is the first thing that is noted. That is the first thing that is analyzed. Yeah, and the second thing is, does the battery catch fire or does it ignite? Yeah, so if there is no short circuiting happening, or if there is no ignition happening, yeah, then that means that the cell or the battery device that is kept for testing here is stable. It is both electrically and thermally stable in these situations, in this situation, and that it is safe to say that it is not going to undergo, or the risk of undergoing short circuiting is very low during real-time operation. Yeah, so that is the aim, that is the purpose of this, is to check the functionality of the cell during this kind of situations, especially when it experiences low resistances. Yeah, and also to check if the cell's internal protection devices is working correctly or not. Right, so that protection device basically helps in preventing the short circuit by isolating the cell. Internally it isolates the cell. Okay, so this is how the short circuit test works. Yeah, so with this, we are done with the abuse tests, and then next we will also go to the aging test. So first we will look at the loss of capacity or the loss of charge due to storage. Okay, so this is done to evaluate how much loss in battery performance occurs due to no usage of the cell or due to isolation of the cell. Okay, so what is done is that a cell or a battery pack, yeah, is first it is first isolated at 45 degrees Celsius in open circuit voltage condition. So what open circuit voltage means is that there is no circuit connection to the cell, or there is no load being applied to the cell. Yeah, and once it is thermally soaked at 45 degrees Celsius, it is then kept at 50% charge or 50% battery capacity, and then it is stored in a isolation unit or a storage unit for a period of up to 30 days. Yeah? And once this particular period of storage is done, so once 30 days is done, the battery device is then removed. Yeah, and then the remaining bit of its capacity would then be checked by a static capacity test. Yeah, by discharging it at 1C, depending upon the capacity that it was originally manufactured at. Yeah, so after this, the permanent loss in capacity, okay, it's called capacity loss. So this is another type of capacity loss which occurs due to isolation. Okay, so capacity loss will be observed. So this is the main criteria. It's basically to see how much capacity has been lost due to extended periods of storage. Yeah, so the same thing can be repeated even for a storage period of 3 months, 6 months, 12 months, and then for a period of even up to 48 months. Yeah, and then seen how and then after that it can be like estimated how much of the performance is completely like lost and how much capacity has been lost completely. Yeah, and it can also be like tested at different temperatures. So with this, we'll be able to understand what is the amount of capacity being lost. Yeah. So this is with respect to storage loss due to storage. And we also have performance loss due to cycling, charging and discharging cycling. Yeah. So again, here what happens is the battery is first soaked at 25 degrees Celsius, or it is kept at 25 degrees Celsius. And then the discharging cycling begins. Okay, so a cycle means one complete charging and then discharging. So continuously, this kind of charging and discharging will continuously keep occurring between 80% charge and 30% charge. Yeah, so it will be discharged till 30% and then charge again till 80%. So this will keep repeating continuously for a period of 22 hours, right? And then after this 22 hours period is complete, it would then be given a break. So the battery is then isolated for 2 hours. Yeah. Then again, after 2 hours is complete, then again for 22 hours, it will experience the same type of cycling. And then this is repeated continuously for a period of 7 days. Yeah. So every 7 days or every alternate 7 days, another pulse test or pulse power test is carried out to see how much internal resistance has changed and how much capacity has been faded and how much power has been lost, performance has been lost within the cell. Yeah. So this is nothing but capacity loss. Again, same similar results, capacity loss. Okay. So this is again capacity loss, but this is due to cycling. So charging and discharge cycling. So upon continuous cycling like this, how quickly does it begin to lose its capacity? So that is the goal of this particular test. Yeah, and this is done to analyze how quickly or in how many numbers of cycles will it have a significant loss in capacity. Yeah. So this is how the cycle life test is done. So this will be repeated for a period of 2 to 3 months continuously. Yeah. And for this, it would usually require a lot of time to test. Yeah. But at the end of this, it would be able to clearly estimate how quickly the cell degrades or how the battery pack degrades. Yeah. So this is with respect to cycle life test. This is the essence of cycle life test. Yeah. Now we'll take a look at some of the testing equipment. So here at Decibels Lab, we have this battery testing system from Newware. So you can see this is the company that has currently provided us the battery testing system. And in this, you're able to test different chemistries of different cell chemistries. So not just lithium ion, but even nickel cadmium or zinc cadmium and so many other types of cells. Yeah. So, and then we use a user interface called as Newware BTS, right? Newware BTS. So BTS stands for battery testing system. And in this, you're able to perform almost all of the tests that we have talked about today, except for thermal cycling and except for short circuiting. So apart from that, you're able to perform all of the other tests. Yeah, including even the aging test. Okay, so this is with the testing equipment that here we have in Decibels Lab, and currently it is being utilized to test cells in different scenarios, in different operating conditions, in different current and voltage situations. Yeah. And here are some of the other cell testing facilities. Yeah, especially from Aether. So this is with Aether. They use the same brand from Newware, but here they also have a pressure and temperature testing chambers here. So these two are like these blue ones. These ones, they are pressure and temperature testing chambers, and even for humidity. Yeah. So here Tesla is having from Arbin. So here the cells are they are tested in much more variety of conditions where they undergo even more vigorous testing. Yeah. And very advanced testing happens in these kind of testing equipment. And then we have also from SignLab. So SignLab is not only for automotive, but for all applications. Yeah. Universal applications. So these are some of the different equipment and different industries that use different type of cell testing equipment. Yeah. So let's take a look at some of the schedule. So basically, this is the user interface for the software which is used by us. Okay, and this is called as a schedule manager. Okay, this is called as a step manager or a schedule manager. Step. Okay, so step manager. So basically, what this means is you can actually set or you can actually predefine what all tests you can perform, right? So here you can see this is the step. This is the step number, and here is the step or test type that you can perform. You can perform so many different types of tests. So constant current discharge and so many other different types of tests that can be performed using this. So this is just a layout. Yeah. And here you can specify what type of test you want the cell to undergo. Yeah. And here you can specify current and voltage limits as well. So whether it's for discharge or whether it's for charge. Yeah. And then you can also mention the recording intervals. So at how many second intervals do you want the recording to occur? So at 30 seconds or at 1 second, 15, 20, or at 1 minute. Yeah, as such. Yeah. But this is just a brief overview at the test step manager of our software. Yeah. And here are some of the testing standards. Yeah. So we had taken, I think most of the standards we had seen today was from ISO, but that's not the only one. So most other commonly used ones are from SAE, Society of Automotive Engineers, one from UL, okay, and also we have from US Department of Energy. So USDOE is US Department of Energy, and these are the years of their establishment. Okay, so like for much more detailed information, you can visit a website called Battery Standards Info. I will type that in the chat box later on. Okay, so but these are the different standards and these are the different years of establishment. Yeah, and the most recent one you can see here is from 2018 and also here from 2016. These are all automotive applications. So these are all mostly confined to automotive applications. Yeah. So of course, ELICERT over here, this one is focused on universal applications. Yeah. So with that, thank you all. Thank you for attending today's session. That is the end of today's session. So I will now end the session now.